Hello everyone, I'm Habiba Farrukh from Purdue University, and today I'll be presenting our work titled S3 Side-Channel Attack on Stylus Pencils Through Sensors. Over the last decade, stylus pens have appeared as one of the most popular accessories for handheld mobile devices. Stylus pens let users write, draw, and make selections in a variety of generic and custom-designed applications with ease, and have several useful applications like note-taking, content selection, art and design, and text input. In this work, we focus on the recently launched Apple Pencil's second generation, which is the stylus pen supported with the Apple iPad Pro. Unlike its first generation, this new version of the pencil attaches to the iPad body magnetically for charging. While this new feature of the pencil has improved users' experience, the changes in the pencil's body have opened the door to a potential privacy leakage. We observed that when a user is interacting with the screen using the pencil, the embedded magnets in the pencil's body have an impact on the iPad's magnetometer. As you can see here, there is a visible change in the magnetic readings when a user writes on the screen. Based on this observation, we present S3, a novel side-channel attack on stylus pencils through sensor data. This attack can be launched by an adversary having remote access to a user's device through a benign application that can collect magnetometer data in the background to infer users' handwriting as they interact with the screen. Here we note that iOS does not allow third-party applications running in the background to access touch information such as position of the pencil tip when a user is writing in the foreground. However, any iOS background application, like a simple benign activity tracking app or a music app, can log the magnetometer, accelerometer, and gyroscope data without needing any explicit user permissions. Therefore, the adversary can collect the magnetometer data from the user's device in the background to track pencil's movement from the magnetic readings to infer users' sensitive information while they interact with the screen using Apple Pencil. In our preliminary experiments, we observed that the magnetic readings experience subtle fluctuations when different letters and words are written on the screen. To infer users' handwriting, an intuitive approach may be to train a learning model to identify useful patterns such as letters, numbers, and shapes from similarities between the magnetic data collected over time for a given set of characters. However, this is not easy since the pencil's magnetic impact changes when it is held at different locations or with different orientations on the screen for a given character. Therefore, to launch a realistic attack, our system must track the pencil's movement when users are writing with their natural handwriting style by holding the pencil in different orientations and on different locations of the screen. Keeping these observations in mind, we design S3 to infer users' handwriting from motion sensors data only. While a user is writing on the screen, we collect the motion sensor data in the background and pass it on to a server. There we perform stroke detection using the sensor data to estimate the start and end of each stroke. To track the pencil's movement, we build a multidimensional particle filter which solely operates on the magnetic readings corresponding to the stroke. The particle state includes the pencil tip's location and the 3D orientation of the pencil represented as quaternion vectors. We randomly initialize the particles representing the pencil location and orientation all over the iPad screen and define the movement model for pencil such that at each timestamp, the particle state is updated based on a human writing behavior model which predicts location and orientation changes based on the last few timestamps. At each timestamp, the particles are resampled based on a weight function that uses the magnetic readings from the sensor and that from a 3D magnetic map of the pencil which we generate offline through war driving and magnetic field reconstruction technique. Finally, the particle filter outputs the tracking traces of the stroke, which are then used by the attacker to guess what the user has written. To evaluate S3, we implemented our system on an Apple iPad Pro running iOS 12.0. We asked 10 users to write letters, numbers, shapes, and English common words and sentences on different areas on the screen in different environmental settings and iPad positions. Here we show some of the tracking results generated by S3. S3's tracking results are human readable and allow an adversary to access users' sensitive data. Overall, an attacker can correctly detect 96% of the letters, numbers, and shapes on average using S3. S3 can also accurately track 93% and 80% of the common English words and sentences written by the subjects. It is also robust against different environmental noise and achieves an accuracy of more than 90% in all of the different environmental settings. Please refer to our paper for more insights and details of our work, and thank you for watching.